You. California dreaming about you.
Hello everyone, today's topic is Raman spectroscopy. Before moving to the Raman spectroscopy, we must know what is spectroscopy. As we know, it is just an interaction between matter and electromagnetic radiation. What is Raman spectroscopy? When a beam of monochromatic radiation is passed through a transparent medium or any substance, the molecule present in the molecule scatters the radiation beam in all the directions. Fraction of radiation is scattered at right angle to the direction of incident B by the molecules. As you can see in this figure, the laser source is emitting the radiation and some of the radiation is scattered. If the incident frequency is nu naught, and the scattering radiation's frequency is also nu naught, then such scattering is called Rayleigh scattering. And if the frequency of scattered radiation is greater or lesser than the frequency of incident radiation, then it is called as Raman scattering. This is what I have told in this definition. Next is the theory of Raman spectra. We know two theories of Raman spectra were there. First is quantum theory of Raman effect and the second classical theory. In quantum theory of Raman effect, let's consider a radiation of frequency nu consisting of a stream of particles called photons having energy h nu. Here h is a Planck's constant. These photons are imagined to undergo collision with a molecule. If the collision is perfectly elastic, here the elastic means no change in energy. When the photons and the molecules are collide, no change in energy is observed. They will deflect unchanged. A detector is placed to collect energy at the right angle of incident B, will thus receive photons of energy h nu. Therefore, radiation of frequency nu as the incident frequency. However, it may happen that energy is exchanged between photon and the molecules. By the collision, such collisions are inelastic, means there is a change in energy. Molecule can gain or lose amount of energy only in accordance with quantum law. Its energy change, delta E joules, must be in the difference of energy between two of its allowed states. That is to say, delta E must represent change in vibrational or rotational energy of a molecule. If a molecule gains energy, delta E, the photon will be scattered with the energy h nu minus delta E, and the equivalent radiation will have a frequency of nu minus delta E by h. Conversely, if a molecule loses energy, scattering frequency will be nu plus delta E by h. The radiation scatters with a frequency lower than that of incident radiation are the Stokes radiation, and then that of higher frequency are called anti-Stokes radiation. Since the former is accompanied by increase in molecular energy and the latter involve decrease in the molecular energy. Here the Stokes radiation is generally more intense than anti-Stokes radiation. Next is the classical theory of Raman effect. When a molecule, we have to just remember that when a molecule is put into a electromagnetic radiation, it suffers a distortion where the positively charged nuclei will be attracted toward negative pole of the field, and the electrons, which is negatively charged, will be attracted toward positive pole. The separation of charges causes the induced dipole moment to be set up in a molecule, and molecule is said to be polarized. Here the induced dipole moment equation is given, where alpha is the polarizability and E is the electric field strength. Okay, when an electromagnetic radiation of frequency mu falls on a molecule, the electric field experienced by each molecule varies with time according to this equation, where E is equal to E naught sine 2 pi nu Vt. Then by applying this electric field strength equation to the above induced dipole moment, we will get another equation number 3. Thus, electromagnetic radiation induces a varying electric dipole moment, which then permits emission of light identical in frequency with that of incident radiation. This is Rayleigh scattering. In addition, molecule undergoes some internal motion such as vibration or rotation, which changes the polarizability periodically. Then the oscillating dipole will be superimposed upon the vibrational or rotational motion. Here the vibrational frequency have taken nu V, which changes the polarizability. The equation then becomes as given in equation number 4 in the next slide. Then here in the equation 4 you have seen A naught is the equilibrium polarizability and beta represent rate of change of polarizability with the vibration. By applying that polarizability equation to the induced dipole moment, you will get the equation number 5. Here you can see by expanding this equation, you will get sine 2 pi mu naught and sine 2 pi nu Vt. And to this we will apply the trigonometric relation, that is sin A sin B half cos AB minus cos A plus B. By applying this trigonometric equation to this equation, you will get this equation number 6. Here in this equation, first term on the right hand side of the equation 6 contain the frequency factor nu, which that of incident radiation. This term is interpreted in terms of Rayleigh scattering. And the second term on the right hand side contain addition of incident frequency nu, the frequency nu plus nu Vt. Thus, the induced dipole moment can also isolate with two frequency, that is nu plus nu V and nu minus nu V. These two frequency are interpreted as vibrational Raman frequency. Here this, in that equation, nu minus nu V and nu plus nu V frequencies are known as Stokes and anti-Stokes lines. And in one thing I have forgotten to tell in that previous slide is Stokes lines are more intense than anti-Stokes radiation. Okay, then next is Raman activity of vibration. It's difficult to say which molecule is Raman active and which Raman inactive. In order to be a Raman active, molecular rotation or vibration must cause some change in the component of molecular polarizability. A change in polarizability is of course reflected by the change in either of magnitude or direction of the polarizability ellipsoid. Okay, here I've taken two molecules, water and carbon dioxide, to accomplish that which is Raman active or inactive. Here you can see in water molecule, here I have considered a asymmetric top molecule, water, whose polarizability ellipsoid is shown in this figure, right? We illustrate A, B, C respectively. The three fundamental modes of vibration stretching for each mode of equilibrium configuration in the center with extreme position to right and left. Here you can see the different modes of vibration. Here you have seen that symmetric stretch mode, where by stretching a molecule while it stretched, its size is increased. On bending, not bending, by compressing, this ellipsoid size is enlarged. And here in the bending mode, bending motion, its shape of ellipsoid which changes most. Thus, if we imagine the vibration of very large amplitude, on one extreme, one molecule approaches a linear configuration with the horizontal axis, while the other, on the right, is approximates to diatomic molecule. Finally, in the figure C, you can see this. In figure C, we have a symmetric stretching mode where both size and shape remain approximately constant, but the direction of major axis changes markedly. And all the three vibrations involves obvious change at least one aspect of polarizability ellipsoid, so they are Raman active. Next, we will consider second linear triatomic molecule, carbon dioxide. These are the three fundamental vibration modes. Here is also a question of Raman active or Raman inactive. So, in figure, we will illustrate the extreme equilibrium configuration of a molecule and their approximate polarizability ellipsoids. The question of Raman behavior of symmetric stretching mode. This symmetric stretching mode is easily decided. During the motion of molecule changes size, so there is a corresponding fluctuation in the size of the ellipsoid. The motion is thus Raman active. And it might be thought that nu0 and nu3 vibration, means below 3 bending and stretching mode, asymmetric stretching mode, are also Raman active because the molecule changes shape during each vibration, and hence presumably so does the ellipsoid. However, both these modes are observed to be Raman inactive. Then, in the same way, we can consider many other examples of example in this way also. And then here you can see in carbon dioxide molecule, in symmetric stretching, there is no change in dipole moment. No change in dipole moment, so it is Raman inactive. But there is a change in polarizability. Therefore, we have said that it is Raman active. In symmetric stretching, there is a change in dipole moment, therefore Raman active. No change in polarizability, therefore Raman inactive. Here also there is no change in polarizability, so Raman inactive. Next is rule of mutual exclusion principle. If a molecule has center of symmetry, then Raman active vibrations are IR inactive, and vice versa, means if it is Raman active, then it would be a Raman inactive. Examples: carbon dioxide. For a carbon dioxide, none of vibrations are simultaneously active in both IR and infrared. Carbon dioxide has center of symmetry. Here it has a center of symmetry, right? If it has a center of symmetry, yes, it has Raman vibration active, then its inverse, Raman vibration, IR vibration will be inactive. Or if Raman vibration are inactive, then IR vibration will be active. And the converse of this rule is also true. If a molecule, both IR and Raman spectra do not have common lengths, then molecule has center of symmetry. That's it. What? Molecule mutual exclusion principle. Then we will consider what is vibrational modes of some molecules and their activity. Here I have taken a simple planar and pyramidal triatomic molecule, AB3 in general molecule, where symmetric planar activity will be R represents Raman and I represent infrared here. Here Raman is active, infrared inactive. Here also, in the same way. And same molecule it was told, Raman inactive, I infrared active, and vice versa. And in pyramidal, you can see here, and their activities also. Any of triatomic molecules you can take like BF3, NH3, etc. Thank you. And you can refer for the more information. These are the reference. And thank you.
Can anybody out there hear me?